All right, so welcome. Today's our first day, so I thought that a good place to start would be to talk a bit about proving things. This is Introduction to Linear Algebra, and the course involves a lot of mathematical thinking, mathematical reasoning, and this thing we like to call a proof. So I thought this would be a good place to start. Try to figure out what the hell is a proof. I know you might have seen proofs before, maybe. But let's just make sure that everybody has really seen a proof or two. The best place to start, I thought, would be with things that everybody knows already. Things like super basic axioms. These would come from your third grade math class or long time ago. Super basic things that you would learn in elementary school, and some super basic facts. For example, I bet you were in third or fourth grade when you first heard the idea that maybe -1 times a -1 is equal to a +1. Right? This is a fifth grade fact. I don't know, whatever, middle school or elementary school. And I'm sure back when you first heard it is, how could that be? You probably thought to yourself, how can that be that a negative times a negative equals a positive? And surely enough, you probably went and asked your teacher, and your teacher probably said, because I said so, boom. Or because two negatives make a positive. Or because whatever. My experience has been that this is never really proven in the mathematical sense, which is kind of unfortunate because it is one of the most beautiful things in mathematics. They say there are only two kinds of people in the world: those who love proofs and those who don't love proofs. Yet. So I think that this being linear algebra, we should get to move you over to this category in case you're in this category at this point. And so that's why I think that starting with your fifth grade math would be an amazing place to start, because it has all the key ingredients. They give you basic axioms, they give you definitions, and you go at it and you create this beautiful poetic proof. That's where I want to start today. So first of all, I want to introduce the basic axioms and definitions from middle school. I'm sure you've heard of these before, but in case you haven't, let me just mention a couple of things. This fancy n here, like that, this is called the natural numbers. And it really means just numbers like this: 1, 2, 3, 4, 5, 6, etc., 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 etc. Notice what it doesn't include. It doesn't include 0, it doesn't include negatives, it doesn't include fractions. It really is just a natural number starting with 1. Hopefully that's enough explanation for you to understand. So every time we say something's a natural number, we mean it's part of this collection. This is set notation. And similarly, every time we say whole numbers, this is a fancy W, and we mean this collection. And also, a lot of times we will write the W, or a boldface W with a double edge like this. This means not just a regular W, it's the natural numbers. Same thing with the N's. We usually put an extra N like this. That tells you it's natural numbers. Z will usually write like this, etc. Q with an extra little bar like that. Those are special meanings. Rational numbers, whole numbers, integers, etc. So this is just so that we learn the vocabulary. In addition to the vocabulary, we should learn basic things. For example, I'm sure you heard this in third or fourth or fifth grade or whatever, the super famous Commutative Law of Addition. Commutative Law of Addition, which makes it, we take it as an axiom. By the way, things that we take as an axiom, we don't prove, we accept. There are a couple of things that we don't need to prove. These are definitions and axioms. Those are given. It's kind of like when you play basketball or whatever. You don't have to prove that you're not supposed to run without dribbling. That's just an axiom. That's a rule. You can't. You got to dribble the ball when you run or stuff like that. These are given things that you don't have to prove or question. You either accept or you don't. If you choose not to accept it, you can still play, but you'll be playing a different game than everybody else plays. In our game, we assume that all our numbers, natural numbers and integers and whole numbers and rationals, will commute. So any number that you have 3 plus the other number, 3 plus 5 or whatever, you can always switch them around in this way. And so we will have commutative law of addition. I made a little symbol to help us remember what this does. The numbers commute as such, and so on and so forth. There's also commutative law of multiplication. There's associativity law, which means you can move the parentheses. Here, the numbers don't move. You have 3 items, 2 binary operations. These are called binary operations. And the question is, which binary operation should you do? For example, if you had 3 plus 5 plus 7, you have a couple of choices, 3 plus 5 plus 7. Being that these are binary operations, you only do 2 of them at a time. So there's a question of whether you should carry on this binary operation first, or should you carry on this binary operation first? That plus or that plus, which one should you do first? And so the nicer way of writing it, this dilemma is to either you put parentheses here or you put parentheses here, meaning you handle those separately. And it turns out that these will always be the same, and that's what the Associative Law of Addition says. I put little wheels here on the parentheses to give you the idea that the parentheses are the ones that move. The numbers stay put. On the commutative law, the numbers move, but not the parentheses. And so I'm not going to bore you with all these. These you learn in high school or in elementary school. Additive identity is amazing. It's a 0. It means that it doesn't change anybody when you add to it, to any of our numbers. 0 plus whatever number is still the same thing. Similarly, there's a multiplicative identity of identity for multiplication. 1 times anything will leave that anything alone. They are additive inverse. This is the definition for -5. Definition is that it kills the 5 and gives you the identity. That's by definition, okay? You don't have to prove it. That's what a -5 is. It's the anti-5. And so similarly, a 1/5. This is the definition of a 1/5. It's the killer of the 5. These two kill each other and give you the identity. Inverses in general are things that kill each other. There's the yin and the yang. And when they kill each other, the only thing that's left is the identity. That would be the number that doesn't do anything to anybody else when you operate by it. And a lot of these come in pairs, one for addition and one for multiplication. That's just the nature of what's typically studied around here. I promise you I'm not going to bore you with all these. I recommend that you understand every single one of these axioms. This means logical implication. If this, then this. So, and every time this is true, this will also be true, and so on and so forth. All right, that's the basic axioms that you learn in 5th grade. Okay, in addition to that, we have a lot of these are actual theorems. The difference between a theorem and an axiom is that axioms you don't have to prove. They're accepted. They're the rules of the game. These are the rules. You can also think about it in terms of music. These would be your musical notes, your chords on the guitar. When you put a bunch of them together, that follows some sort of logical pattern. It creates some logical conclusion, and the whole package is called a theorem. A theorem is a collection of axioms and definitions put together in a logical way to lead to an incredible conclusion that is necessarily true, undeniably true, beautifully true, and convincingly true. And that's what we usually call the proof. The proof will tell you whether the theorem is true or false. And so it is also usually true that you take any real number, and if you multiply it by 0, you get 0. Now think about it. It might seem like a naive statement or an unnecessary statement to make, but it's actually not true for things that don't follow our axioms. I'll just give you a really quick example. If you take infinity, you learn in calculus, infinity times 0 is actually not necessarily equal to 0. It's an indeterminate form. So this is not always true, but for any number that follows, for any kind of number family that follows our entire collection, we will see that this entire collection leads to the undeniable conclusion that any one numbers that fit that collection, that must be that when they multiply by 0, they get killed and you get 0. And so on and so forth. These are theorems you've heard many times. Negative times negative is a positive, not just for 1, but any negative number times a negative number will give you the positive version of it. You also heard that it doesn't work for addition. If you take a negative plus a negative, you don't get a positive. You get the same sort of sign. You get a negative. And it's interesting to note why. Why are all these things true? And so as a proposition to start our class here, to start our amazing linear algebra class, I thought that we could take just a couple of these axioms and try to play some music with them, put them together and see how they For example, explain why a -1 times a -1 is equal to +1, right? Or other things like why is it that when we multiply fractions, all you do is multiply the bottoms? Or why is it that when you add fractions that have the same denominator, all you do is add the top, not the bottom? I contend, I'm proposing that everything that we did in 5th grade is based on these axioms, and you can prove every single one of them. So that's where we're at today. I thought just for fun, what we could do is we could take some of those basic concepts that you learned in 3rd grade and just see how much things we can prove. Okay, so yeah, let's do that. All right, so just a quick note on the notation. Whole numbers, these ones here are a subset of the integers. That's these ones here. Just so we're on the same page, we'll write the notation this way. Whole numbers are a subset. This is how we write subset of the integers. That means that every single one of these numbers that is a whole number is also in this collection. And if they weren't, the way we negate elements, for example, also more notation, 0 is not a natural number. How would you write that? So we write it like this. 0 is not an element of the collection of natural numbers. This is how we write 0 is not a natural number. So you'll see a lot of these symbols. They're pretty common. Element of, contained in, or contained in backwards, or not an element of, etc., etc. Don't be afraid of these. They're just shortcuts for saying that when an element is contained in a set, or a subset is contained in a larger set. A set is contained in a larger subset set. Okay, so anyways, real simple examples. We're gonna start off real easy again. Other examples of things that we can do based on the axioms. So we're going to assume that we know the addition table just for the natural numbers. We're going to assume that we know the times table just for the natural numbers. So here we go. For example, if I asked you how much is 3 plus 3, you could say, oh, well, that's equal to 6. And then right next to it, always you want to have a statement and you want to have why. Why is that so? So that we have almost like a 2-column proof. The statements go like this and the whys go here. And that way everything you say is super, super tight. As tight as it could be, logically speaking. And everything is explained. And it would be so, so beautiful when you explain everything. Believe me, you will feel good because it's part of your DNA. You're wired to love logic. Remember, there's only 2 kinds of people in the world. Those who love proofs and those who don't love proofs. Yeah, so here I'm going to explain why. Why? Well, because of the addition table axiom. That was something that I don't have to prove. That was something we assume. By the addition table, we assume that we know how to add all natural numbers. Now here, how about this one? How much is 0 plus 3? Well, you might say 0 plus 3 is equal to 3. Why? Can you say by the addition table? Well, in this case, you'd be completely wrong if you did that, because 0 is not a natural number, so it wouldn't be explained by the addition table that explains how to add natural numbers. And so this would actually be false. Very, very false. You could say that it is so by this one. This one explains to you how to add by 0. It's the additive identity. The additive identity tells you every single time you got a natural number and you add 0 to it, you get the same thing. And this doesn't just work for natural numbers. This is for naturals, rationals, every real number, every complex number that we do. You can always add 0 and no harm done. It stays the same. So I could say this is true by additive identity axiom. Boom. Now, what if I wanted to add -3 plus 5? How much is that? Well, it's definitely not by the addition table. It's definitely not by the additive identity. Then how do we do that? It turns out that none of these will actually work. None of your axioms will work to do this. And so we have to think about something else. And that's a beautiful thing, because now we're starting to do our class. Our linear algebra is about taking axioms and definitions and putting them together like music so that you can get an amazing result. I'll come back to this one later. Other examples of things that we might or might not know. For example, how do we multiply? How much is 3 times 5? Well, you could say that's equal to 9, but then I'm going to ask you to explain why. Well, since these are 3 and 5 are in fact natural numbers, and we have the times table that works for natural numbers, then of course this is justified just by times table. The times table explains that. But if I had -3 times 5, well, it turns out that the times table doesn't apply here because these are not natural numbers. Specifically, the 3 here, the -3 is not a natural number, so we actually don't know how to do that. What about 0 times 5? Well, it turns out 0 is not a natural number, so you can't say by times table, and so we actually don't know that either. -1 times -1, well, we actually don't know that. You might think you know, maybe some of you do, but we're going to take the most beautiful road this way, where we assume nothing other than the things that we said we're going to assume, nothing else. Gandhi said, happiness occurs when what you say, what you think, and what you do are in harmony. So I'm going to say I'm only going to assume my axioms, nothing else. And that's what I'm going to do. So here I'm going to be honest about it and say I don't know why -1 times -1 is +1, and so on. All right, that's the gist of it. We make 2 columns on everything. Oh, I repeated some of these examples, but it's okay. We get more practice. This is the addition table. This is the I don't know, because we have never done that before. But maybe we're ready for this. I think maybe we're ready for this. You guys want to do this? Yeah, no, don't worry. We can handle this. Let me think. I do know, based on the times table, on the addition table, I do know that. By the way, if you've never seen an addition table, it might look something like this. Maybe I've never drawn it before, but it goes like this. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And of course, it goes on forever. Dot, 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 dot. And this tells you 1 + 1 is 2, 1 + 2 is 3, 1 + 3 is 4, 1 plus. I can't believe I get paid to do this. Insane amounts of money to do this. 4, 5, 6, etc., etc. So you just basically tells you how to add these two numbers. If you wanted to add 2 + 3, you just go down that row, and it gives you that. That's the addition table. So that's why the symbol is like this. And we will assume that we know the entire thing all the way to forever for natural numbers. Okay. So, but based on this, I know that 5 could be broken up as a 2 plus a 3. How do I know that? Well, because of the addition table. The addition table tells me that, in fact, 2 plus 3 is equal to 5. So the addition table tells me that I could do it backwards. 5 is equal to 2 plus 3. If I just said 2 plus 3 is equal to 5, I can certainly do it backwards. All right, then what I could do is I could say, oh, wait, there's a way that we can shift the parentheses so that I could just add the 3 and the -3. Who says you could take these parentheses and kind of like put wheels on them and move them this way so that now they're over here? This is about moving the parentheses. The numbers stay the same, but the parentheses moved. Well, this would be the associative law of addition. That's what it would guarantee that. Now, shoot, I only wish I knew how to add 3 plus a -3. 3 plus a -3. But wait a minute, I got no business adding a -3 if I don't even know the definition of what the hell is a -3. Wait a minute. So we go back to our source here, our axioms and our definitions. Do we know what a -3 is? Right here. Sorry, I messed this up. Don't worry about it. It's okay. I got it. Don't you worry. So a negative number, like a -5, means it's the 5 killer. It kills the 5 and gives you the identity. That's what these negatives are by definition. They're killers of the yin and the yang version of each other. So I know that the 3 and the -3, they're the yin and the yang. They kill each other and give you the identity. So this gives me 2 plus 0. The 3 and the -3 became 0. And I know exactly why, because these are additive inverses. Boom. And now I only wish I knew how to add 0. But wait, do we know how to add 0? What is the definition of 0? Oh, 0 is the guy that does nothing. It's the identity. It does nothing to anyone. So therefore, this could be equal to just simply 2, because 0 is the additive identity, and I know how to add by 0. Nothing happens, and boom. Now by transitivity property, check this out. This one is equal to that one. That one is equal to that one, because I'm looking at these equal signs, right? That one is equal to that one. That one is equal to that one. So therefore, the first one is equal to the last one by what? Again, we have here transitivity property. This tells you that if A is equal to B and B is equal to C, then A is equal to C. And so therefore, 5 plus a negative 3 is equal to 2 by the transitivity property. Boom. You see why they pay me? Do you see why they pay me insane amounts of money? This is why they pay me. So beautiful, so logically penetrating. It's super good. It should feel really, really good to see every single step like this developed to perfection. You are wired to love this sort of stuff. It's just like humans are wired to love chocolate and sugar and all the things that are bad for us, except this is good for us. This feels so good in the mind. It's like healthy food for the mind. So perfect. And so this is what we would call a proof. I just proved that 5 plus negative 3 is equal to 2. And I did it by walking you through a very, very logical and convincing argument based on axioms and definitions. And no BS, no wishy-washy stuff. Things that I said I was going to assume. I said, I'm going to assume these things, and I'm going to see what I can prove. And sure enough, I did it. That's how a proof works. All right, now let's continue with a couple more examples. 10 plus a negative 2. So based on the previous one, this should be a piece of cake now because I've already given away the solution. First of all, I know that I can do 10. Sorry, I can break up 10 as an 8 plus a negative 2. Sorry, shoot. I'm falling in love. I can't think straight. All right, so therefore, this would be the addition table. The addition table tells me that 2 plus 8 is the same thing as 10. Those are all natural numbers, so that part is good. I replace a 10 with this, and explain it perfectly by the addition table. I usually use G for given. Okay. Now I'm going to slide the parentheses over. So I'll slide the parentheses over, and this will be 8 plus 2 plus negative 2. And remember, sliding the parentheses is all about the associative law of addition. Okay. And of course, a 2 plus a 2, those are born killers of each other, the yin and the yang. So that's the additive inverses. By the way, sometimes if you want to be a little extra fancy, instead of using the actual acronyms for this, you can actually use the symbol. You can make a beautiful proof by doing this. The symbol that I invented for this, the yin and the yang, with the plus on it. Boom. Additive inverses. Okay. Of course, this is 8 plus 0. I know how to add by 0. That's the additive identity. Additive identity. Or again, you could use a symbol for additive identity, which is like the 0 with addition. You could do that if you want to be extra fancy. Yeah, why not? It's a beautiful day to be extra fancy today. Let's do that. Additive identity, the additive 0. And there you go. By transitivity property, now the first one is equal to the last one, and that's a beautiful proof right there. But there's more to it. But wait, there's more. Let's do the same thing, but for multiplication. Now I have to learn how to multiply a regular old number, natural number, such as 10, times a fraction. Holy cow, we've never done, pretend you're a little kid, you've never done this before in your life. Think, how the hell am I going to do that? Well, first of all, you got no business multiplying by a fraction if you don't have the clear definition of what the hell that fraction is. So let's go to our source, our definition. What the hell is a fraction? Here, this explains to me what a fraction. This explains what a fraction is with a 1 on top. Oh, a fraction is a multiplicative inverse. Okay, that means they're killers of each other, the yin and the yang. And when they kill each other, they give it the multiplicative identity. So 1/5 was born to be the 5 killer. 1/3 was born to be the 3 killer. 1/7 was born to be the 7 killer. The yin and the yang, they kill each other and just give you 1, the multiplicative identity. So based on that definition, I know that 1/2 was born to be the 2 killer. So here we go. I could take that 10 and I could break it up as 5 times 2. Why can I do that? Well, that would be by times table, clearly. And then I could say, okay, I wish I could move these parentheses over so that I could just rearrange them here on the 2 and the 1/2. Oh, but wait, when you have 3 things multiplied here and you have the parentheses, you can actually move the parentheses over there. We have something called Associative Law of Multiplication. Where are you at, baby? Right here, Associative Law of Multiplication. You can move the parentheses through the times binary operation. And so I could say that this becomes 5 times 2 times 1/2. And that was by Associative Law of Multiplication. But wait, there's more. What is 2 times the 1/2? Clearly, those are killers of each other, so they're multiplicative inverses, and they give you 1. They're multiplicative inverses. Okay, and of course, the 1 times 5, I know how to do that. That's multiplicative identity. And yippee-ki-yay, I just proved with beautiful reasoning, tight reasoning, perfection in reasoning, I just proved that 10 times a half is equal to 5. Step by step by step. So beautiful. But wait, there's more. When I open this up and I show you the comparison between, look, adding 10 and a killer and an additive inverse of 2, how similar it is to taking 10 and multiplying times 1/2, the multiplicative inverse of 2. Look, the first step was the addition table. Over here, the first, and breaking up that 10 so that I could kill that. The first step over here was the times table. This is the same as that, except this is for addition, this is for multiplication. But wait, there's more. The next step was Associative Law of Addition. And over here was Associative Law of Multiplication. It is exactly the same step, one for addition and one for multiplication. The next step was additive inverses. These things kill each other and give you the additive identity. Additive inverses. Here is multiplicative inverses. It's exactly the same step, except for one's addition, the other one's multiplication. And here, this one is the additive identity. It goes away. The multiplicative identity goes away. So this shows you how similar these two ideas are. And it turns out that adding is so similar to multiplying. They're just binary operations on certain sets. And so one of the beautiful things that linear algebra will do is we'll take this concept and say, wait a minute, if I can learn concepts here in addition, and I can figure out what is the secret sauce here with the addition, maybe I can apply them to other operations, and all my thinking and all my theories and all my discoveries here can translate into other worlds with other binary operations. Maybe in the next example, I could have matrices, which is exactly what we're going to do in this class, a bunch of matrices. And a lot of these proofs that you did in 5th grade, well, I don't know if you did them. Where I come from, they didn't show me these proofs, but whatever. A lot of these type of reasoning will transfer over, not just to addition, but to multiplication, but it'll transfer to composition of functions, to matrix multiplication, and a million other things. The beautiful thing about this is it abstracts the key pieces of information, and once you abstract them, you can apply them to 1,000 different places. It is a way of becoming so efficient at learning knowledge, because once you learn it here in this world, you've already learned it in a different world. That's what's beautiful about it. So this does a lot of important things. It shows you, first of all, it shows you examples of real nice outlines of real proofs using axioms. And second, it shows you how powerful it is when you abstract that idea and how you can apply one idea to several different places. Okay? All right, talk is cheap. Let's do a couple more and then we'll call it a day. Yeah? I don't want to overwhelm you. Too much good stuff. It's like too much chocolate cake. So let's take it easy. All right, it's a beautiful day because today you're going to learn to multiply by 0. You thought you knew, but no. How do you know how to multiply 10 times 0? We don't know. So let's see if we can crack this one. Okay, so here we go. How much is 10 times 0? Well, let's see. Start off with not knowing, so therefore let's start off with something else. I know 0 plus 0, that's equal to 0. The reason for that is the additive identity. When you add 0 to anything, it doesn't change the other thing that you're adding it to. So 0 plus 0, we'll leave it unchanged by additive identity. 0 is like adding water to something. It won't change the color. Okay, the next thing I know is I know I can multiply both sides by 10, so I could say I could write the same thing over again. 0 plus 0 is equal to 0. And I could slap a 10 on both sides. So I go 10 times the left side and 10 times the right side. Now, who says you can go around multiplying both sides of an equation by something else? Well, of course, we have the famous Cancellation Law of Cancellation Law of Multiplication says you can multiply both sides by a number. Okay, so I did, and of course, I'm justifying it with an obsession to perfection here. Cancellation Law of Multiplication. Okay. Now I know it. You know this other famous trick here. When you have a number and you multiply it times a binomial in here, you can take this and you can distribute it. That's super famous. Everyone knows that. It's 10 times 0 plus 10 times 0 is equal to 10 times 0. And that, of course, is called the distributive law. You remember that from 5th grade. Then what I could do is I could take my 10 times 0 plus my 10 times 0 is equal to my 10 times 0, and I could add something to both sides. To the left side, I will add a, whoops, try to change colors here. To the left side, I will add a negative 10 times 0, and to the right side, I will add a negative 10 times 0. And of course, the thing that allows me to add stuff to both sides is the Cancellation Law of Addition. It says you can add stuff to both sides. And so I will justify it beautifully, like I always do, Cancellation Law of Addition. Okay, now I'm thinking that what we could do now is move these parentheses, move them over here so that we can take the 10 times 0, which we don't know what it is, but we know that if you add it to the killer of it, 10 times 0 plus the opposite of it, these will kill each other and give you 0. Same thing with these ones. 10 times 0 plus its killer will be 0. And so we will have something amazing in just about 2 more lines here. So I'm moving the parentheses. 10 times 0 plus negative 10 times 0 is equal to 10 times 0 plus negative 10 times 0. And I'm justifying it. And I'm justifying it. That's called Associative Law of Addition when you move the parentheses. Now, this and its killer give you 0. This and its killer give you 0. So this will be 10 times 0 plus 0 is equal to 0. That is by additive inverses. Of course, additive inverses, they kill each other. That's what they were born to do. And then adding 0 to anything will leave it alone. So that's because it's the additive identity. So that gives me a 10 times 0 is equal to 0 by additive identity. And yippee-ki-yay. We proved it. We got that. We started off with this crazy statement, which was out of nowhere, like divine inspiration. How would you know that you should start here? 0 plus 0 to prove this. This doesn't at the first sight, it doesn't look anything like this, and yet this is a really good place to start. Additive identity, slap a 10 on both sides, distribute, follow every single thing here with an obsession with perfection in reasoning, perfection in logic, and boom, the goods are delivered. 10 times 0 is equal to 0. Yippee-ki-yay, proof. And of course, you could package this whole thing and turn it into a theorem. And we could call it the zero multiplication theorem. There's nothing special about 3. The same proof would have worked for 3 or for 5 or for every natural number. Infinity, no, because it doesn't follow any of our axioms, or not all of our axioms. Everything else you can say by you packaged it all into one package, and we called it the zero multiplication theorem. So next time you can just skip all these steps and say, for example, if I wanted to do 7 times 0, oh, it's equal to 0. Why? Because the zero multiplication theorem. And this is like the song, and these are like the chords. All the chords packed together give you that song, which gives you just, you can package it into just one line, basically. All right. Good. It's beautiful, right? Now, the moment you've been waiting, why is a negative 1 times a negative 1 equal to what? And what is it equal to? Well, here we go. Let's start off with something amazing and creative. So let's start off with negative 1 plus 1. I know what that is when you add them. Those are additive inverses. And that is why when you add them together, you get the additive identity. Okay, it's crazy that you would start that way. This doesn't seem like the right place because you're multiplying here. This is multiplication, yet I'm starting here with adding them. And you might wonder why. Well, because of divine inspiration. I know this will get it done. Okay, and the next thing I'm going to do is I'm going to go negative 1 plus 1 is equal to 0. And I'm going to do something to both sides. I'm going to multiply the left side by negative 1. And I'm going to multiply the right side by negative 1. And I'm going to justify it with an obsession with perfection. Cancellation Law of Multiplication allows me to multiply both sides by a number. Okay. Next thing I'm going to do is I'm going to take this one, and I know the distributive law allows me to distribute that. So this could become negative 1 times negative 1 plus 1 times negative 1, and that's equal to 0 times negative 1. Okay, and all I did was the distributive law on the left side. Next thing I can do would be, I think I know how to multiply by 1. Multiplying by 1 is the easiest thing. What happens when you multiply by 1? Pretty much nothing. 1 times a number will give you the same number because it's the most harmless number that you can multiply with. It's a multiplicative identity. It works on negatives, on positives, on all our real numbers, even complex numbers. So then I could say negative 1 times negative 1 plus negative 1. And that's equal to 0. What? Okay, so on the left-hand side, I use multiplicative identity. That's what got me that this is equal to that, multiplicative identity. On the right hand side, I used the previous theorem, the one that we did earlier. 0 times any real number gives you 0. So 0 times any real number gives me 0. So that's what we packaged into one nice packaged theorem. It's called the zero multiplication theorem. Okay. Now what? Well, now I'm going to do something more creative. Not really super creative, but a little creative. I'll take the left side and I'll add a 1 to it, and I'll take the right side and I'll add a 1 to it, and I'll justify it because I love justifying things, because I love perfection in reasoning. Cancellation Law of Addition says I can add any number to both sides. I added a 1 to both sides. I'm going to slide these parentheses over so the 1 and the negative 1 can do their killing of the yin and the yang. Watch how beautiful this is going to turn out to be. Negative 1 times negative 1 plus negative 1 plus 1. Sliding the parentheses over to those. That's equal to that. So all I did is Associative Law of Addition. Then I do negative 1 times negative 1 plus 0 is equal to 0 plus 1. That's Additive Inverses. And of course, 0 does nothing when you add it to it, so that gives you 0 times negative 1, and that's equal to 1 by Additive Identity. And you know what time it is? Yippee-ki-yay time. Yippee-ki-yay. You know what's after that? Boom. It's a beautiful proof, and this shows me how to multiply a negative 1 times a negative 1. It tells you that every single time you have a negative 1 times a negative 1, by the logical consequences of all our axioms, it must necessarily be that negative times a negative is a positive. That right there, my friends, is a proof. That's why they pay me insane amounts of money. And it explains so much. Again, it explains things from 5th grade, but it explains the nature of our current course, linear algebra. A lot of things there are statements like this where we'll take extra pleasure in proving and understanding why things work the way they do. All right. Well, it's been a pleasure. I think that's good for one day. Let's stop here while we're ahead. Peace. We'll see you next time.